Okay, we'll keep going from Tuesday. I'm guessing this is it for who's going to turn up for the lecture. So on Tuesday, what we'd done was we kind of finished pushing that source and sink together, and we generated this new building block flow that was we're calling the doublet. And then what we did was we added a uniform flow to that doublet, and we were able to show that well, actually very easily, we were able to show that the separatrix of that circle, the separatrix associated with that doublet and the uniform flow was just a circular profile, as given by that equation on this slide. And you can see, I guess the most important point from this was that the radius of the circle was uniquely related to the strength of the doublet K, and also the magnitude of that oncoming uniform velocity U infinity. So, however confusing it was deriving or conceptually trying to consider or to derive that doublet, we should at least just be able to go forward and use that as a new building block flow. And then we replaced that circular separatrix with a solid body, and we, hey presto, we'd simulated the 2D inviscid incompressible flow over a cylinder. And moving on from that point, also on Tuesday's lecture, I showed you that actually in cylindrical polar coordinates, the stream function for that, and we'll come back to this in today's lecture, hopefully, I showed you that the stream function for that flow around a cylinder, which is just the stream function for a doublet plus a uniform flow, could be written in this quite convenient and compact form if we wrote things out in cylindrical polar coordinates. And the nice thing about this, what I was trying to show you but maybe didn't come across, was that in certain situations that cylindrical polar coordinate system can really work in our favour. And the example of this on Tuesday's lecture was when we were trying to calculate the pressure distribution around that cylinder. So what we first did was use that stream function in cylindrical polar coordinates to give us the components of velocity, the radial component of velocity UR and that azimuthal component of velocity on the surface of the cylinder. And immediately that was very tidy for us because we know that the surface of the cylinder is a streamline, and we know that the flow has to be tangential to a streamline. So we know that that normal component of flow is going to be 0, so we knew that radial component of velocity had to be 0. So I guess the only point I'm trying to make is that in certain situations, different coordinate systems are going to really work in our favour. And in this instance, that cylindrical polar coordinate system really simplifies the algebra. You'll eventually get to the same solution, all right? It will just take you a couple of pages longer, I would imagine, if you do it in Cartesian coordinates. But anyway, by substituting the velocity on that surface of that cylinder into Bernoulli's equation, and then substituting Bernoulli's equation into the equation for pressure coefficient, we got this very nice analytical form for the distribution of pressure around that cylinder. Is everybody, how many of you have done your aerofoil lab now? Maybe half of you? So is everyone starting to feel at ease with the meaning of pressure coefficient, CP? None of you who are prepared to admit it. So does that mean that none of you have a clue what CP is? Or So that pressure coefficient is really a way, it's like a dimensionless pressure force that's acting on that surface, okay? And I know that you come across all these dimensionless groupings and you don't know what possible use they might have. But if I just spoke in terms of the actual dimensional force acting on that cylinder due to pressure, that would be absolutely a function of the properties of the fluid, and it would also be a function of the velocity of that fluid, U infinity. Now, the nice thing about talking in terms of pressure coefficient is that I could get a more general result that would then be applicable. If I knew the pressure coefficient around this particular cylinder, I could then go and apply that reasonably confidently to a cylinder that was operating at a much different velocity or in a different fluid. So for your aerofoil lab, you calculate pressure coefficient distribution around the aerofoil, or you calculate the lift and drag coefficients. That means that from that laboratory, you'll get a lift and drag coefficient for that aerofoil. And if we then wanted to build an aircraft that used that aerofoil, and that aircraft, say, had a weight of 2 tons, I'd know that I need to generate 2 tons worth of lift, and I could use that lift coefficient that you calculated from your laboratory to then scale that aerofoil or work out how much area or what size that aerofoil would need to be in order to generate that lift for a full-size aircraft. So you're doing a scale model test to get that coefficient, and then you can use that coefficient at full scale to actually build something of use, all right? So that's a bit of a detour, but the pressure coefficient is along similar lines. It's a dimensionless quantity that should be applicable to regardless of the flow velocity or the type of fluid within reason. So then right at the end of Tuesday's lecture, I introduced this concept of the velocity potential, which maybe in hindsight was a bit of a silly thing to do when I only had a few minutes left. It's discussed on page 26 of your lecture notes, but hopefully most of you got the main point here, was that the stream function was a way of defining a flow in such a way that it automatically satisfies continuity. So if you want to think of the potential function in very simplistic terms, it's just a way of defining a flow field so that it automatically satisfies irrotationality in the flow field. So rather than satisfying continuity, it satisfies that irrotational condition. And what do we know if what equations of motion are we satisfying if we satisfy that irrotational condition? Momentum equations, right? I think one of you said that, or you were just clearing your throat, and I'm wishful thinking again. So that equation for irrotational flow is just du dy minus dv dx is equal to 0, and I hope that you can all see that if I defined a flow, if I defined the potential function in this following way, so that u equal, the potential function is phi, I'm using this Greek symbol phi, and if I define the velocity so that u equals d phi dx and v equals d phi dy, I hope you can see that if I substitute d phi dx for u in that equation for irrotationality and d phi dy for v in that equation for irrotationality, I hope you can see that that's automatically satisfying that irrotational condition. Can you all see that? So that equation at the top is just going to become d phi dx dy minus d phi dx dy, which is just something minus that same something, which has to equal 0. Okay, so it automatically satisfies that irrotationality condition. And then we discussed, well, that's all very well, but what about continuity? And when we substitute this new definition for the potential function into that equation for continuity, then what you end up with is something that you should recognize as the Laplacian of phi, or the Laplacian of that potential function. So in order to satisfy continuity, I don't understand that, but this slide is incorrect, but it was correct on Tuesday's lecture. That should be the Laplacian of phi equals 0 at the bottom, not the Laplacian of psi. I have absolutely no idea how that happened. All right, so in order to satisfy continuity, the Laplacian of that new function, the potential function, must equal 0. Okay, so this is your kind of cheat sheet, and I'm going to give you a few more cheat sheets of things that you kind of need to wrap your head around. So we've got for this course, we have to satisfy continuity and momentum, and we can distill satisfying those momentum equations down to just satisfying that irrotational condition. So the stream function was defined in such a way that it automatically satisfied continuity. the potential function is defined in such a way that it automatically satisfies that irrotational condition. And then conversely, in order to get the stream function to satisfy that irrotational condition, the Laplacian of that stream function must equal to 0. And in order for the potential function to satisfy continuity, that Laplacian of that potential function must equal 0. So algebraically, you understand all of that, right? You just don't yet understand what the purpose of all this shenanigans could be. Is that correct? Okay. So, and I would hope that it would become a little bit clearer, but I think I'd be lying if I said it would be by the end of today's lecture, but it will become clear. And I'd also be lying if I said you were going to thank me for it. But we'll see. It is useful and kind of elegant for us. So we can define U and V in terms of any velocity field that has a U and a V. We can define it in terms of the stream function, or we can define it in terms of the potential function. And if we can define it in terms of both, it automatically satisfies all of our equations of motion. Do you agree? If I have a building block flow and I can define it in terms of stream function, then I know it satisfies continuity. And if I can define it in terms of the potential function, then I know straight off the bat that it satisfies those momentum equations. So it's kind of like a sanity check in a way. And it's also a useful exercise in kind of telling us what this potential function might be representing. So let's just go back exactly the same way as we defined those building block flows in terms of the stream function. Let's just have a go at nutting out expressions for them in terms of this new function, the potential function. So for this, the simplest one is this uniform parallel flow. We've got flow coming from left to right. I know that the horizontal component of velocity u is just equal to u infinity. And I know that that vertical component of velocity v is just equal to 0. So what I can do now is make use of my definition for the potential function and just substitute d phi dx for u in that equation and d phi dy for v. And I now get d phi dx is equal to u infinity and d phi dy is equal to 0. So if I want to write an expression for this flow, I want phi equals something to define this flow. What's the next step? Come on, I'm testing your goldfish-like memories. It's exactly the same step that we used for defining the stream function for these flows. Huh? Yeah, right. So if d phi dx is equal to u infinity, then phi must equal u infinity integrated with respect to x. So phi is going to equal u infinity x plus some unknown function of y. And likewise, if d phi dy is equal to 0, then phi equals 0 integrated with respect to y, and even I can do that integration. So phi is just going to equal some unknown function of x. And by comparing those two simultaneous solutions, you can see that they're only compatible if that function of y, f1, is a constant, and if that function of x, f2, is equal to u infinity x. So what we end up with is that the potential function for this horizontal flow is just equal to u infinity x. So phi is equal to u infinity x. We'd already shown that the stream function psi was equal to u infinity y. So those blue arrows on this figure are showing the direction of the flow, so they're really showing streamlines, which are lines of constant stream function psi. If I plotted onto this figure lines of constant potential function phi, they'd be oriented in the way shown on this slide. They'd actually be orthogonal or at right angles to those streamlines, okay? So right off the bat, I have to tell you that lines of equipotential, to me, are kind of harder to wrap my head around than lines of equal stream function. I know that lines of equal psi are just streamlines. Those lines of equipotential are a little bit harder to think about physically. So But anyway, we can define this flow in terms of that potential function phi. And we could do a similar thing for the source flow. If you remember, a source flow was just a volume flux issuing from a point in space. And that, from that point where that volume flux issues, we know that the flow just propagates out radially. So I've got a radial component of velocity UR, but since that flow is purely propagating radially, I know that that azimuthal component of velocity U theta is equal to 0. And we also showed when we derived that equation for a source that if I consider a circular control volume and I apply conservation of mass, I know that the radial component of velocity is just the radial component of velocity UR is just a function of is the inverse of that radial position. It's just given by Q on 2 pi R. This is exactly the same as the previous derivation we did. That's just through a conservation of mass. So in this case, it makes sense to work in cylindrical polar coordinates rather than Cartesian coordinates. So you won't remember, all right? But in lecture 3, right at the end of lecture 3, we went through, we started off with a Cartesian definition of the stream function, and I showed you very simply how to convert from that Cartesian definition into a cylindrical polar definition. So likewise, you can express the potential function also in terms of cylindrical polar coordinates. So there's a relationship between UR and d phi dr, and a relationship between U theta and d phi d theta as given here. And you can reassure yourselves of that by following through that same methodology from lecture 3. So anyway, if you take my word that that's how you express the potential function in cylindrical polar coordinates, you can see that I can just substitute d phi dr for UR, and 1 on R d phi d theta for U theta. And again, if I integrate, I can get an expression for that source in terms of that potential function. So if d phi dr is equal to Q on 2 pi R, I know that phi is equal to the integral of Q on 2 pi R with respect to R. And you know that the integral of 1 on R with respect to R is just log R. So phi just becomes Q on 2 pi log R plus some unknown function of theta. And again, I know that d phi d theta is equal to 0, so phi is just equal to the integral of 0 with respect to theta, which is just some unknown function of radial position. It's quite straightforward, right? I mean, it's quite straightforward to follow your way through these steps. It's not straightforward trying to work out why I'm doing it, I guess. So, and then obviously the only way these expressions again are compatible is if f, that function of r is Q on 2 pi log r, and if that function of theta again is a constant. So we just end up that the potential function for a source is equal to Q on 2 pi log r. And again, we can compare that to the expression that we got for the stream function, which just told us that psi was equal to Q on 2 pi theta. So again, those blue arrows are the direction of the flow. So they're really showing streamlines or lines of equal stream function psi. If I plot lines of constant potential onto this plot, which is shown by the red curves, again, you get this sense that lines of constant potential function are orthogonal or perpendicular to the streamlines. Do you see what I'm saying? By the way, I wouldn't be able to look at those equations and know that they had that form shown on this slide. I'm just plotting them in MATLAB, okay? And I'm plotting one in blue, and I'm plotting lines of equal potential function in red, and I'm just making the observation that they appear to be orthogonal to each other. But we can prove that very easily in just one moment. And you could do the same thing for the source, and you know, not surprisingly, you get a similar pattern, just that flow being sucked inwards at the source. So actually we can prove that lines of constant stream function are orthogonal to lines of constant potential function. And I guess this is the key. This is the key to why the potential function might be useful to us, I guess. So it's very it's very easy to write out an equation for a line of constant stream function. We've done it a few different ways, but for now, maybe one of the simplest ways is just to consider a small change in that stream function psi. So just write out an expression for d psi, some small change in the stream function. So if psi stream, what's the stream function a function of? X and y, right? So if the stream function is purely a function of x and y, what does d psi equal? Yeah. So it's going to equal d psi dx dx plus d psi dy dy, all right? Because it's only a function of x and y. Then, if I want the equation for, if I want an equation for a line of constant stream function, what do I know that d psi is going to be equal to? 0, right? So what I can do is substitute my definition for the stream function into this. So u equals d psi dy. I know that v equals minus d psi dx, so d psi dx equals minus v. And then I'm going to equate d psi to 0 because I'm looking for a line of constant stream function or a streamline. So I just end up with this expression that we've come across previously, the equation for a streamline, that u dy is equal to v dx, okay? And I can rearrange that and just say that dy dx is just equal to v on u, okay? So dy dx for a line of constant stream function is equal to v on u. So my notation's a bit weird here. I'm just saying that the gradient of a line of constant stream function is equal to v on u. So I can also do the same for a small change in the potential function. The potential function phi is also only a function of x and y. So I can write out the same expression for d phi equals d phi dx dx plus d phi dy dy. I can substitute in my relations or my definition for the potential function. So u is equal to d phi dx, u is equal to d phi dx, and v is equal to d phi dy. And again, a line of constant potential function, d phi is going to equal 0. So I get u dx plus v dy is equal to 0. So u dx is equal to minus v dy. So dy dx is going to be equal to minus u on v. Yeah, minus u on v, okay? So the gradient dy dx for a line of constant potential function is equal to minus u on v. So what we've got is two expressions. One is the gradient for a line of constant stream function. One is the gradient for a line of constant potential function. And what you should, I guess you should see the answer staring you in the face there, really. But what we can write is that the gradient for a line of constant stream function is equal to 1 on the gradient of a line of constant potential function, which tells us what? Tells us that they're mutually perpendicular, okay? So a line, I guess I'd kind of shown it anecdotally through those few derivations of the uniform flow and the source flow, but this, I guess, is a more formal proof of the fact that a line of equipotential constant phi is going to be orthogonal, perpendicular to a streamline or a line of constant stream function. Okay, so let's just kind of let's build up another one of these cheat sheets, which I suggest you kind of print out and pin on your wall during SWOT-VAC. So we've got a definition in Cartesian coordinates for the stream function at the top. and we've got a definition for the potential function given below. And in Cartesian coordinates, that's very straightforward. I've also given you definitions for those in terms of cylindrical polar coordinates. For the stream function, I showed you where that how we get to that cylindrical polar definition of the stream function. You should be able to follow through that same methodology to reassure yourselves of that, the cylindrical polar definition for the potential function also. And what you can see is that there's a relationship between phi and psi, okay? I don't know who came up with the two Greek symbols that are used here. I would have probably preferred that they sounded a little different. Psi and phi is very challenging for me to keep saying up here, right? But anyway, you can see if you compare, we've got two equations for u, all right? We've got u equals d psi dy, and u is equal to d phi dx. So therefore, there's a relationship between the stream function and the potential function. D psi dy is equal to d phi dx. And you can see that there's a similar relationship if I equate those vertical components of velocity. So d psi dx is equal to minus d phi dy, or minus d psi dx is equal to d phi dy. So there's there's an obvious relationship between those two functions. We've kind of shown that because we've shown that they're perpendicular to each other. And you could also write out the same relationship in cylindrical, or similar relationship in cylindrical polar coordinates. If I equate the radial components of velocity, I get that 1 on r d psi d theta is equal to d phi dr. And if I equate those azimuthal components of velocity, I'm going to get that minus d psi dr is equal to 1 on r d phi d theta. So I guess I should have put something on these slides. Maybe I will before I put them on LMS. I think these are useful reference slides that you kind of just clutch in your hands as you're working your way through, following your way through work solutions from this course or tutorial problems. But for now, just know that we can define very simply that relationship between phi and psi. Okay, so that actually allows us to convert between talking about stream function or potential function very simply. Before, what I did was I went all the way back to defining a flow in terms of the u and v components of velocity and just re-derived an expression for that building block flow in terms of the velocity potential. But actually, now we've got a means of just converting, right? So if we go all the way back to the beginning of the lecture, we had this equation for the stream function of a doublet plus a uniform flow, which is an equation for the stream function of a flow, a 2D envisaged incompressible flow around a cylinder. So what I can do is very simply, using those relationships between psi and phi, I can just convert algebraically from this equation for the stream function to get an equation for the potential function. So from that starting point, we have an expression for the stream function. It's in cylindrical polar coordinates, so I should use those conversion or those relationships between stream and potential function in cylindrical polar coordinates also. And actually, what I'm going to do is make use of the first of these, this one that I'm highlighting. So I can write that 1 on r d psi d theta is equal to d phi dr. So, and I can just substitute my expression for psi into this, okay? So 1 on r multiplied by that equation for the stream function differentiated with respect to theta is equal to d phi on r. So there's only two things I need to do to convert. I need to differentiate something, and then I need to differentiate something, in this case with respect to theta, and then I need to integrate whatever's left, in this case with respect to radius. So differentiating that term in the square brackets with respect to theta is pretty straightforward. The only function of theta in the square brackets is sine theta, and I know that the differential of sine theta with respect to theta is just cos theta. And then all I need to do now is integrate everything on the left-hand side of that equation with respect to r. Does that make sense? I've got d phi dr equals something, so phi is going to equal that something integrated with respect to r. What am I doing there? I'm absorbing that 1 on r into those square brackets, so nothing that need worry us. So phi is equal to that term in the square brackets integrated with respect to r, and you should see that the integral of a squared on r squared with respect to r is just going to be minus a squared on r, and the integral of minus 1 with respect to r is just going to be r. So we end up with this very simple expression for the potential function for that same flow. So it's quite easy. I guess the only point I'm trying to make is it's quite easy to express all of the flows that we've been dealing with in terms of the potential function or the stream function if we felt that way inclined. Okay? So we have a potential function now for that flow around the cylinder, and I could, to complement that stream function that we have for the flow around the cylinder, and I could plot. If I wanted to, I could plot isocontours of constant potential function onto that flow around that cylinder. And again, as a sanity check, all of those lines of equal potential function should be perpendicular to those streamlines, which are the grey lines on this figure where they cross. So I guess just as an aside here, you've all been, how many of you have started working on the assignment already? Oh, less than I would have expected. So that probably tells me how many of you are actually rocking up to those workshop sessions. But anyway, those of you who've started, actually maybe that half show of hands means that one person out of the team of 2 has started on the assignment, and the other person has started on an assignment for control systems or some other subject. And good tactic right now, but terrible during exam time, I would imagine. So anyway, most of you have started, some of you, half of you, have started writing codes that will plot streamlines, okay? You're effectively releasing particles in flow fields, and you're tracking where those particles go using Eulerian schemes or more efficiently using an RK4 advection scheme. So my question is, how would you modify your RK4 or Euler code to plot lines of constant potential function rather than to plot lines of constant stream function? This is just an interesting aside. You don't have to do this for your assignment. I just thought some of you I foolishly thought some of you might be interested. So how do you think you'd do it, given that those lines of constant potential function are perpendicular to lines of constant stream function? Well, it's good to know then that I'm not, because it took me a while to figure it out, and I just was, I'm always, often when that happens, it's because I'm being dumb. Yes, you can, but then do you remember how those gradients are just related to, so it's actually that relationship between those gradients and the U and V components makes life very, see, you would have got there. I should have just, I should have asked you all ages ago. It would have saved me time, okay? So at present, what you're doing is you're releasing particles and you're just tracking where they go in time, okay? So you have an equation for the u component of velocity, which is the rate of change of that x position with respect to time, and you have an equation for that v component of velocity, which is the rate of change of that y position with respect to time. So really, to a first order approximation, you can see that gradient dy dx is just equal to v on u, okay, when we're tracking lines of constant stream function. So if we want to track a line that's orthogonal to that stream function, rather than moving u multiplied by time in the x direction, we need to move v minus v multiplied by time in the x direction and u multiplied by time in the y direction. Does that make sense? What I'm saying doesn't make sense, but the figure makes sense, right? You can see that if you just rejig your codes ever so slightly, probably some of you have even done this by accident, by just getting things muddled up, you'll be tracking lines of constant potential function, okay? So for a line of constant potential function in your equations where you've got a dx dt, you know rather than dx dt equaling u, it now equals minus v, and rather than dy dt equaling v, it now equals u, and you should be able to release particles and then track lines of equipotential or lines of constant potential function. Okay, so I guess the reason we introduce the potential function, or the reason I introduce the potential function, is so that I can introduce the complex potential function, okay? So the torture never ends, right? It's like, you know, it's like those Russian dolls, I guess. But the potential function has a use for us, right? It has a very nice, elegant use for us. And again, I guess I haven't really... The potential function will make coding these problems actually much more elegant for you in MATLAB if you can be asked to do it, all right? It will, it really improves the tidiness and the elegance of these problems and really helps us with the later stages of this course when we tried to nut out flows around error floors. So we've got equations for the stream function, we've got equations for the potential function, and we had this relationship in Cartesian coordinates between the stream function and the potential function. Does anybody, have you seen that relationship at the bottom there? Have you come across a set of partial differential equations that look like that before in any other mathematics or physics course? No, I'm guessing that's a resolute no. I think what it is it's a resolute I don't remember, because I'm pretty sure that you should have come across equations that look like that, at least in mathematics course. Let me jog your memory more. Have you heard of the Cauchy-Riemann equations? You have, right? You must have come across that in a mathematics course. No, yes, some of you have, right? So those Cauchy, you would have seen it written this way, that dB dy is equal to dA dx, and minus dB dx is equal to dA dy. That relationship that we have between the stream function and the potential function has some nice kind of mathematical meaning, and it allows us to do some kind of neat tricks, all right? So they're called Cauchy-Riemann equations. They're named after these two guys, okay? And Cauchy, at least, you know, they were proud of him. They were proud enough of him in his native France to even put his face on a stamp, okay? We show you stuff like this because it's supposed to be inspirational, you know? If you do well in math or engineering, you'll get your name on a stamp. None of you even care about that now because you want to be like billionaires. You want to be Elon Musk and have whole planetary systems named after you. But this used to be enough for scientists, really. You know, if you got a dimensionless number named after you, you were a made man for life. And, you know, a face on a stamp or a banknote, fantastic, okay? But anyway, so these equations are quite well known, and the mathematicians that kind of recognise this are also quite well known. Not obviously by any of you, but in France at least. So the interesting thing is that if you've got a set of partial differential equations that meet this, that obey this relationship, okay. And I should say here that B and A are both functions of x and y. if you have a set of partial differential equations that meet this relationship, then you can express a complex solution to the problem, okay? So you can write that W, which is some complex solution, is just equal to A plus IB, where I is that complex unit, okay? So, see, this just gets better and better, doesn't it? Now we've got complex numbers as well, which I'm sure you all hated that as well in your mathematics courses. So, and we'll show you why. I'll show you why, why we can say that. But if we've got a set of partial differential equations that satisfy those Cauchy-Riemann relationships, you can write that W is equal to A plus IB. So more precisely, A and B are functions only of x and y. So I can write that W, which is a function of this complex ordinate, x plus iy, is equal to A, function of x and y, plus IB, which is a function of x and y. And you've come across this complex coordinate x plus iy before, right? Oh, come on. This is like pulling teeth. What did you call x plus iy when you came across it before? Z? Did you call it, someone say Z? Yes, right. So you do remember something about complex numbers. So we can write that W, which is a function of Z, is equal to A plus IB. And you remember that Z equals x plus IY. Or we can also write Z. This is just a complex number refresher here, nothing new. You can also write Z in terms of that complex exponential, okay? So you can use Euler's relationship, another Euler's relationship, and you can write that Z is equal to R e to the I theta. You've all seen this before. It's like zero feedback here. You've all seen it before. I'm going to tell myself you have. Okay, so if you refer back to our definitions for the stream and potential functions, what this means is that I can write a complex function W, which I'm going to call the complex potential function, which is a function of that complex coordinate Z, is just equal to phi, the potential function, plus I psi, I multiplied by that stream function, okay? So for any 2D inviscid incompressible flow, which by definition I should be able to define in terms of a stream function and a potential function, I can also write out a complex solution for that flow in terms of the complex potential. And I'll hopefully show you why that would be useful. Okay, so for now, just let me try to show you that there's a relationship between those Cauchy-Riemann equations and that expression for the complex potential, okay? So what I'm going to do is start off from that equation for the complex potential, and I'm going to try and arrive at those Cauchy-Riemann equations. And it's very simple, okay? And then you'll realize why, if you have a relationship of partial differential equations that meet that Cauchy-Riemann relationship, that you can express things in terms of this complex potential. And anyway, there's some basic mathematics here that will get us used to using complex numbers again. So the first thing you do is just write out an expression for the partial differential of W with respect to x and y. So I can write that del W del x is just equal to dW dz. W is actually a function of that complex coordinate z. So I can write del W del x is equal to dW dz multiplied by del z del x. And we know that z is equal to x plus iy. So differentiating that complex coordinate is very simple. Okay, the differential of x plus iy with respect to x is just going to be 1. Okay, so you can see that del z del x is equal to 1. So we get, straight off the bat, we get this neat relationship that del W del x is just equal to dW dz, okay? And I can do the same by writing an expression for the partial differential of W with respect to y, and we just get dw, del w del y is equal to dw dz multiplied by del z del y. And again, I can differentiate z with respect, I can write out the partial differential of z with respect to y. Z is equal to x plus iy, so the differential of that with respect to y is just going to be equal to I. All right? So I've got dw dx is equal to dw dz, and I've got del w del y is equal to I dw dz. So what you should be able to see here is that I've got a dw dz on the right-hand side of both of those relationships. So I can actually write that del w del x is equal to 1 on I del w del y. Does that make sense? Okay, it does, and you're just furiously writing things down. So del w del x is equal to 1 on I del w del y. And then I can also write out another expression for del w del x, right? I know that w is equal to phi plus I psi. So I can write that del w del x is just equal to d psi dx plus I, sorry, d phi dx plus I d psi dx. And dw dy is equal to d phi dy plus I d psi dy. And you see that if I just substitute those expressions 2 into that relationship that we nutted out at the top there, I get something that's quite useful, okay? So I substitute for del w del x, and I substitute for del w del y, and I get this relationship shown at the bottom here, or now shown at the top. And you should see that that 1 on I multiplied by I del psi del y on the right-hand side, that I is just going to cancel out. And then also, again, this is just gymnastics with complex numbers, right? 1 on I is equal to I on I squared, which is equal to minus I. So I can write 1 on I as minus I. And then if I equate the real and the imaginary parts, if I equate the real and the imaginary parts of the left-hand side and the right-hand side of that expression, I get d psi dy is equal to d phi dx, and d psi dx is equal to minus d phi dy. And I'm sorry, I'm just being lazy and saying d for partial derivatives, because I'm getting tired of calling this all out, okay? So from that complex for that complex function to be true, you can see that you automatically arrive at that Cauchy-Riemann set of relationships. Okay, so the two are interrelated. If you have a if you have a potential function and a stream function that's related in this way, then I can automatically write out a complex potential function for them also. Okay, so I think I'm going to leave it there, and we'll pick up on we'll pick up in tomorrow's lecture. So, just to give you a heads up, so you don't go away hopelessly depressed, that complex potential function, I know that like no one hates complex numbers more than I do, all right? And I wouldn't just introduce it just for the fun of it, believe me. It really does make life a lot simpler for us as we move forward in this course. And you're welcome to keep working in terms of the stream function and U and V components if you want, but the complex potential will make life easier for us. and the drag kind of goes through the roof when I mean, this is a store, right?
Yeah, this is the store.
And the drag goes through the roof. So and there's like the kind of key thing is the key thing for an aircraft design is the lift to drag ratio. And you can see that also stops being favourable once you exceed that stall point.
Yeah, I got it.
Yeah.
And in order to have the optimum angle of attack, I need to follow what Kevin told us to try something by using some kind of algorithm to find angle of attack. And after that, is there something anything we don't wrong?
I don't think so. I mean, what I would do is then plot the lift to drag ratio, which is
right now we don't know anything about that.
And then I think what you see is that you'll see that there's a region where Vanguard at the top where you've got quite favourable lift to drag coefficients, and then when you exceed that stall, I would expect lift to drag coefficient to come right down. So in this situation, like, we're generating a huge amount of drag and only generating maybe twice as much lift. So the lift to drag ratio is terrible.
I can't do yes like that as well.
So that means that if you had an aircraft that weighs 10 tons, you need to generate 5 tons of thrust.
Yeah, that's horrible.
Yeah. So I mean, when it's 1-to-1, you're back to being like a ballistic rocket.
I think you don't even have to do all the factors.
I think there's another class coming.